Welcome back to the second last session of this semester. The aim this week is to try to finalize the discussion of generative adversarial networks. And that means also that we will have to look back at some of the definitions which we made last week. Thereafter, we are going to take a look at the diffusion models with some selected examples, and that is going to, in a way, prepare those of you who are interested in studying further diffusion models. And as we mentioned previously, these diffusion models play a very central role in many of the modern software developments in machine learning. They play the fundamental role in developments of extremely popular applications like ChatGPT. So having an understanding of what diffusion models are actually doing is something which is very important. Now, we will, in this course, we will not go into the programming details of diffusion models. This is a set of lectures which will be updated for next versions of this course. So please stay tuned when it comes to details concerning diffusion models. Now, there are several readings which are really good. So there is a paper the original paper by Sol Dickstein et al. On deep unsupervised learning using non-equilibrium thermodynamics. Then there is an excellent and very pedagogical paper by Calvin Luo, and I have actually borrowed quite a lot of material from that paper. That has been an inspiration for the development of my notes. And then there is a paper by Kingma et al., and Kingma is one of the people who developed variational autoencoders. And this paper is also a very pedagogical read. And to remind you of these works by Kingma et al., there is also a very pedagogical paper by Kingma and Welling, and these are the people who actually developed variational autoencoders. And there's quite some connection between variational autoencoders and the diffusion models. So let me give you a quick reminder from last week about the general adversarial networks. So the GANs is a deep neural network, which normally consists of two networks, a so-called generator network and a discriminating one, or just called the discriminator. And through several iterations of generation and discrimination, so as a competition between the two, where the generation or the generative part of the network, which could just be a simple neural network, same as a discriminator, the competition between these two is so that the generator can be viewed as a neural network or a deep learning method, which is trying to generate copies of a set of input data which it is trained against. And the discriminator is going to discriminate between the original data and the data which are then being produced by the generator. So in the simplest version, the two networks could just be two standard neural networks with a given number of hidden layers and parameters to train. And the generator which we have trained, that can then be used to produce, for instance, new images. So the generator part is the one which then, when it has been trained, has implicitly obtained a description of some data set. And you can say that this is an implicit derivation of a probability distribution, which allows us to generate new images. So just to quickly remind you of some of the things which we did last week, and then we are going to jump back to the slides from last week a little bit, just to remind ourselves of some other technicalities. So in general, a discriminator estimates the probability of a given sample coming from the real data set, and it attempts at discriminating the trained data by the generator and is optimized to tell the fake examples from the real ones. And then we say that the discriminator tries to distinguish between real data and those generated by the above-mentioned generator. Whereas the generator outputs synthetic samples with a given so-called noise variable, which we also have labeled with an H as a latent variable. And it is trained to capture the real data distribution in order to generate samples that can be as real as possible. And that's why the generator, when things have been trained, can be seen as a way to determine new images, and implicitly then to have function which mimics a probability distribution. So at the end of the training, the generator can be used to generate, for example, new images. So in this sense, we have trained a model which can produce new samples, and we have implicitly defined a probability distributions. So last week we discussed what kind of data GANs are used on. So they are generally a form of unsupervised machine learning, but they also incorporate aspects of supervised learning. So internally, the discriminator sets up a supervised learning problem. Its goal is to learn to distinguish between two classes of generated data and the original data. So the generator then considers this classification problem and tries to find adversarial examples. That is, examples which will be misclassified by the discriminator. And if you then look at it, you can also view a GAN architecture which also works on something which is called supervised, semi-supervised learning. And a semi-supervised learning is actually a learning environment where you include both labeled and non-labeled data. And so these are the kind of three most common settings where we would use a GANs. Now, the thing I wanted to bring back a little bit is the basics of a setup of a generalized generative adversarial network. And the basic model is trained by setting up what's called a generator and then the discriminator. And we define here a probability P of H, which is used by the generator. And this is often a probability which is given by you. So this is a probability distribution which is easy to train and easy to sample from. And it's often given by even a uniform distribution. You can use a Gaussian or you can use a binomial, depending on the type of data you're training. And that produces a uniform output for this latent variable H. So remembering a little bit about the standard autoencoders, we have a so-called latent space where we did the dimensionality reduction. And often this latent space is trained and set up so that it's much smaller than the original space X. So we define also a distribution for the generator, which we call a P of G. And this is the generator distribution of the data X. And finally, we have a distribution P of R, which is the one over the real samples X. And the optimization is then done by calculating these quantities, one for the discriminator network, and this could be just a plain neural network, and you generate events according to this distribution P of R. So you would need actually to have a model for that. And meanwhile, you give some fake examples which are then trained and set up according to this distribution, which often is representing a smaller space, and it can be as simple as a uniform distribution. And the discriminator is expected to output a probability D, which is then given as an input by this G of H, together with a D of X, as you see here. And this is something which we want to have to as close to zero, where we just minimize the difference between 1 and the probability for D generated by the generator. So at the end, we end up with what is called a min-max game. So where we try to minimize G and maximize D. And this is a struggle between these two expectation values, where we generate events according to 1, the real data. So this X is supposedly following a probability which mimics the real data. And then we have a probability here, which is generated by a probability distribution of our own choice, which often may actually mimic the specific situation which we have. And these are the two quantities which we are setting up. Now, I wanted to go a little bit back to what we did last week and remind you of some practicalities and technical concepts which we put up last week and which we have derived earlier. So let me just jump back to the Jupyter notebook from last week and remind you of some of the technicalities which we did there. So one of the things which we did, and let's just scroll slowly down here till the quantities which we used in variational autoencoder. So one of the quantities which is used as a metric to assess whether the probability distribution we are setting up is as close as possible to the one which we want to have, or suppose you have this probability distribution, then one of the metrics is called the Kullback-Leibler divergence, which then is given by the expectation value of the log of the real probability divided by the one which we are setting up as a model. So in variational autoencoders, this probability Q here is the one which defines the encoder and translates the real data into the latent space. So one of the drawbacks with this KL divergence is that it's asymmetric, and this has been normally improved upon by introducing something which is called the Jensen-Shannon divergence, which is then defined as the average of the Kullback-Leibler divergence, but where we now have, instead of Q, we have P plus Q divided by 2, and then we take the next quantity where we take the ratio between Q and P plus Q divided by 2. And this is a quantity which is then symmetric in the two probabilities, P of X and Q of X. And the thing which we did last week, when we run the code, there's a code example. If we then scroll down here, there was a short repetition last week from concerning variational autoencoders. And then one of the things which we did was simply to run a calculation with a generative adversarial network. And these are codes which were applied to the standard MNIST data set. So at the end, we ended up with a training and best values, which we end up having then, which when we did the training, if we just scroll down here, one of the things which we observed when we did the training of the generative adversarial network, so let's just move slowly down here, was that the loss function for the functions d of x and the fake one, they actually approach when equilibrium has been reached and the network training has been attained. Then there is a ratio between d of x and d of generated g of x, which approaches 0.5. So one of the things which we're going to do now is actually to take a look at why should these approach this value of 0.5. So last week we just saw that as a result of the runs. But now let's go a little bit back to the equation which we are trying to optimize in order to understand why the optimal values upon the finalization of the training is equal to 0.5 for these two functions d produced by acting on the real data and d on the fake data here. So let's go back to the slides for this week and take a closer look at what are the optimal values for this quantity d. So what we are having when we now look at these expectation values, we're actually calculating this loss function, and this is the quantity which we want to optimize. So the question then is, what is the optimal value for d? From the numerical samplings which we had, the optimal value after a given number of iterations was approaching 0.5. And let's see now why we should get 0.5. So this is the function we want to optimize. And then we ask ourselves, what is the optimal value for this quantity? So the best value for this function, when we now introduce this variable, so this x tilde is nothing but this d of x. A is just a short for this probability, which reflects the real data. And B is the probability, which is now produced by the probability distribution, which we have defined in order to set up the generator. So if we now look at the integral which you have here, you can actually safely ignore the integral sign here because x is sample of all the possible values. So we can actually take the derivative inside this function. So if we now redefine everything which we have here as a function f of x, and you see now that this f of x is actually given by the same function which we have in here, just relabeled in terms of these functions a and b. So if we now take the derivative of this function f in terms of, because now we want to find the optimal value for d of x. So we take the derivative of this function, and by taking the derivative, what we see now is that the best values, when you look at this equation here and you want to drive this to 0, which is a pretty common approach, then what we find is that the best value of the estimator is given by the ratio between the real probability divided by the real probability plus the one which we have defined for the generator, which is supposedly a much simpler probability to generate samples from. So once the generator is trained to its optimal PG, gets very close to the real probability distribution. And when this quantity P of G is equal to P of R, this ratio becomes equal to 1/2. And that is something which we saw when we run the calculations from last week, and which I just reminded you of now by bringing back the calculations from last week. So at the optimal values, what happens then, and there are several instructive outcomes which we can look at. So with both G and D at the optimal values, then we have that the probabilities P of G should be equal to the probability of the real data. So that means that we have trained this P of G to be equal to the probability distribution which defines the real data. And this D with a star here, which is the optimal value for D, is equal to 1/2. And when we then plug that into this function here, then we know that we have P of R equal to P of G. So that simplifies some of the calculations here. And we know that also that if you look at this quantity here, since we assume that P is normalized to 1, then this just becomes equal to 1. So this is integral. And then we have a log of 1/2 here. And then that means that when we add these two terms, we simply get -2 times log 2. So when we now look at this divergence, this Jensen-Shannon divergence, which we included, then we can actually compute this divergence by just plugging in these optimal values. And that means that the divergence here, which is used as a kind of metric in the optimization, is then given by log 4 plus the loss function calculated at the optimal value of D. And this loss function, what does it actually quantify? So this loss function of GANs that quantifies the similarity between the generative data distribution and the real sample which we have by the so-called Jensen-Shannon divergence. There are other quantities, so this divergence actually requires that you evaluate an integral here. This divergence is actually less used, and there's something which is called the Nash equilibrium condition, which is more used in training GANs. But this gives you a kind of feeling of how we can actually set up the training of a generative adversarial network. And in this specific case, what we have is that the cost function or the loss function is then given by this Jensen-Shannon divergence -2 times log of 2 here, if we just follow the algebra which we have been setting up here. So that means that the best G, the one which would be the optimal that replicates the real data distribution, leads to a minimum of this function. So if we have the best G, then this Jensen-Shannon divergence is actually equal to 0. So the best loss function is the one which actually leads to -2 times log 2. So these are just some simple mathematical observations which we can set up when we are training a generative adversarial networks. Now, the generative adversarial networks, the way they are set up, can often lead to very slow and unstable training. It can be hard to reach that equilibrium point, which you saw in this simple example here. So this will be when a typical example of when equilibrium has been reached. And remember now that these data were trained on the MNIST data, which are the handwritten numbers. And you can see now the result of the generator when we now are picking some specific samples. So you will see after one epoch, this doesn't exactly look like number 9. After 2 epochs, it's getting closer to number 9. And then after something like 100 epochs, we actually have a result Sorry. This is the prime allergy season. Now, you can now see that the numbers which are generating start resembling numbers which we can identify with those which were in the original data set. But still, this is not optimal. So GANs can actually be very slow to train. It can be very difficult to reach equilibrium. And because often each model is actually updating its cost independently with no respect to another player in the game. And updating the gradients of both models concurrently doesn't exactly guarantee a proper convergence. Now, there's another problem, and this is a problem which we also have with any training of these networks, and that is the problem of vanishing gradients. So when the discriminator is perfect, then what we are guaranteed is that d of x is equal to 1. And it's actually d of x is equal to 0 when it's trained on x coming from the generator. That means that the loss function falls to 0, and we end up with no gradient to update the loss during learning iterations. And one can encounter actually situations where the discriminator gets better and the gradient vanishes fast. So GANs may actually face problems like if the discriminator behaves badly, the generator does not have accurate feedback and the loss function cannot represent the real data. And if the discriminator does a great job, the gradient of the loss function drops down close to 0 and the learning can become pretty slow. So these are typical problems which apply to the kind of straightforward implementation of GANs, which we discussed last week, using the programs which you can find in the textbook by Rashka et al. So we adopted in the lectures the programs which are set up in the textbook by Rashka et al. From chapter 17. Now, there is a lot of debate, and you will find in chapter 17 of the textbook of Rashka improvements to the standard GANs. And one of these improvements is something which is called the Wasserstein distance, which we will not go into details here, but I refer to the textbook of Rashka and this chapter 17, where these improvements are actually discussed. So the instead of using this Jensen-Shannon or even the simpler version, this Kullback-Leibler divergence, or what is normally used is called the Nash distance. What is commonly done nowadays is actually to use what's called the Wasserstein distance. So this terminates in a way our discussion of generative adversarial networks. It was meant mainly as an introduction to the topic. And what we did was simply to discuss one of the simplest implementations, which is not exactly where the forefront in the research of generative adversarial network stands. So for codes and more, there are actually lots of examples in the textbooks which we have chosen for this course. So you have in PyTorch, you have an example of using the Wasserstein distance. In the textbooks by Babok and Bali and Foster, you will find TensorFlow examples. So in the textbook of Foster, it's chapter 4, which is the relevant one, whereas in the textbook of Babcock and Bali, it's actually chapter 6. And there you can find several implementations and improvements of the simpler cases which we have been discussing. So GANs, the way we presented them, have many of these problems with also vanishing gradients. We have problems with the achieving equilibrium. And also there is a typical problem which one encounters in this type of data sets is that sometimes the dimensionality of the data set which we have can be artificially high, whereas the real representation of the data set is normally represented by a much lower dimensional set of representations. And that can be one of the, drawbacks in training these adversarial networks. Now, this is a big research field, and if you go online, if you, for instance, look at this article here from 2021, you will find several discussions on where the research front is moving. And as you probably have noticed now, if you go back to the original papers back in 2014 and 15, when the original ideas were introduced by Goodfellow et al., you have a kind of feeling that 10 years ago is actually what you might describe as archaeological time in machine learning. Now, one of the models which has now gained a lot of interest are so-called diffusion models. Now, diffusion models, they also build upon what we have seen earlier with variational autoencoders. So the kind of tricks which we used with Bayes' theorem, defining a posterior probability, marginal probabilities, and then setting up a encoder space and a latent space, and then setting up the decoder. These are quantities which we are going to use again. But let me give you some of the basic overarching motivation for diffusion models and what they actually implement mathematically. So they are mathematically, instead of having a plain autoencoder, which a variational one, which encodes the data through a probability distribution into a latent space and then decodes it in order to train a model which is going to give us a best possible representation of the final probability distribution. The variational autoencoder is now changed by a chain of encoder functions, which are then given by the standard Markov chain, which follows from diffusion theory. So remember now, or you may have seen it if you've taken a course in, let's say, statistical physics or transport theory or topics like that, or an advanced course on Markov chains and Monte Carlo samplings, is that the physical process of diffusion is intimately linked with a Markov chain. You can actually derive the equations for diffusion starting with a Markov chain. So the basic idea here is actually to use Markov chains and make small steps in what you might call loosely time. And these steps are then done so that you can perturbatively change the parameters of the probability distribution which are setting up. And so the models were actually then introduced back in 2015. And historically, what we have seen when we've been looking at many of these types of generative models, from Boltzmann machines to variational autoencoders, via GANs, and now diffusion models, are two kind of conflicting objectives which we want to strike a balance between. One is tractability, which means essentially that you have a simple distribution which is easy to use, and you can generate new data from that probability distribution easily. In general, we know that the probability distribution which we are studying are multidimensional ones, and they can actually be almost intractable, even if we have an analytical expression for them. And then we have flexibility. So models that are tractable can often be analytically evaluated and easily fit to data. So just think of a Gaussian or binomial distribution or Laplace distribution. However, these models are often unable to describe data which may have rich data sets and complicated relations, and also be multidimensional and complicated distributions. And then, on the other hand, models which are flexible, they can actually be tailored to fit structures and arbitrary data. So like when we set up the Boltzmann distribution, we made a model for this phi, and this phi could then be something like a binary model, which we discussed in detail when we had our discussions on Boltzmann machines a month ago. The problem then is the calculation of the normalization factor. But even this function phi of x can be almost intractable itself. So computing the normalization factor can, in general, be pretty complicated. So evaluated training or drawing samples from such flexible models typically requires very expensive Monte Carlo processes. And this is something which we already have experienced when we discuss Boltzmann machines and variational autoencoders. Now, the diffusion models, they actually have quite some flexibility. So they're very popular because they have several interesting features. They can allow for exact sampling. We'll come back to that. There's an easy multiplication with other distributions in order to evaluate a posterior. And this is, again, a manipulation of different probability distributions using Bayes' theorem. And then the model log likelihood and the probability individual states can actually be evaluated cheaply. So the original idea is actually to use a Markov chain to gradually convert one distribution into another one. And this is an idea which is used in physics, in particular in statistical physics, where one studies processes out of equilibrium. And these are normally modeled in terms of different Monte Carlo samplings. So you would have a typical sequential Monte Carlo set of samplings. And diffusion models build a generative Markov chain, which converts a simple known distribution into a target data distribution using a diffusion process. So a Markov chain is a way to represent the process of diffusion. And rather than using this Markov chain to approximately evaluate a model which has been otherwise defined, you can actually define the probabilistic model as the endpoint of a Markov chain. And since each step in diffusion chain has an analytical valuable probability, the full chain can actually be evaluated analytically. So learning in this framework actually means estimating small perturbations to a diffusion process, and estimating these small analytical tractable perturbations is actually more tractable than explicitly describing the full distribution with a single non-analytical normalizable potential function. Now, furthermore, since the diffusion process exists for any smooth target distribution, this method can capture data distributions of arbitrary form. This sounds almost too good to be true. But let's try to look at some of the mathematics of these types of models. So what we are going to do now is just quickly switch over to the whiteboard here and take a look at some of the defining equations for the process of diffusion and Markov chains. So we are going to switch over to the whiteboard now. So let's do that. So let us remind ourselves of some of the basic equations for a Markov chain. So if we think of a probability distribution, and let's call this probability for P of X. So this is perhaps the final probability. And if we have a continuous process, this is something which can be rewritten in terms of a transition probability, which stands for us moving to X, starting at X prime. So this is the previous probability. And we are making a step, beta, so this is a parameter, which now tells us, how the stepping is being performed. And then we have an original probability in P of X prime. So what this is saying is that we have a so-called transition probability, which is this quantity here. And this is our original probability. And this could be the probability at an initial time or an initial position X 0. Now, I'm not defining whether X could represent a position in space or whether it represents time or whatever kind of variable it can represent. So if you look at the discrete form of this probability distribution which we have, we can then replace X with a P of I. So this would be a state of the system. It could be a specific position in all the available positions which can be mapped out. And we will simply write this as a sum over all the previous positions. And then we have this probability distribution, which is now given often in terms of a stochastic matrix. And we would write this as a Tj multiplied with the original probability P of j. You will often also see this one rewritten in terms of a Tij, which is given by T of j going to I. This is a common notation which you may encounter in the literature. So this is normally called a stochastic matrix. And this stochastic matrix has the property that if we look at the column vectors of the matrix, and if we sum over all these, then we would have a T of j equal to 1. Similarly, P of j is a probability, which means that this is also meant to be normalized. So if I sum over all the probabilities which we have for being in a specific state, this also sums to 1. Now, a Markov chain is a process where the new probability, which we have here, or the new state of the system, depends only on the previous one. Now, the way we can set up this process now is that you could think of this in the following way, and this is the way we are going to actually implement this when it comes to the diffusion models. So we could now think of this probability distribution, which we have, this P of I, to represent the state of the system at a given time t. So I here is a specific state the system can be in. This could be a specific position or a specific state which does not need to correspond to an actual position in space. So this is a specific state which you can reach, and that has a given probability. And then this probability distribution, or the stochastic matrix which we defined, this can often be assumed to be independent of t, or it could have a t dependence. So this could have a dependence on the time t minus t prime. And what we would do then is actually to rewrite this process in terms of, and now let us in the equation here assume that this Tij is not depending on time. So we would then have a sum over Tij, and then we would multiply this with a Pj at the time t prime. So that means that if I make one time step and I start at t prime, the first one, which we call a t0, or it could be an x0 or whatever kind of variable you're dealing with. So this would be our initial distribution, and that would be a well-known distribution. So that means that we would have a Pj of t0. And then we can think of making one step, and then we have a Pt of 1, which is simply given by the sum of Tij multiplied with Pj of t0. Then we can write this in a more compact notation. So instead of writing a specific state, I, we can write a vector which represents all these states. So we can now think of a vector at the time t, which is simply given by all these probabilities. So we would have a P0 at t, a P1 at t, and this goes all the way down to the final position or the final state the system can be in. So in general, this n is an infinitely large number. So this, if we now replace everything or in terms of a more compact vector matrix notation, what we would have then is a vector P of t, which can be rewritten in terms of this matrix multiplied with a t prime here. So if we look back at this Pt of 1, this is now equal to t multiplied with Pt of 0. So what we can assume then is that this Pt of 0 is a quantity which we know. And if we now look more closely at this type of process, what we have is that we can now set up this for a time t of m, and this t of m is now given by t acting n times on this p t0. So the process of diffusion, when it reaches equilibrium, what happens then is that if we take the lim of m goes to a final time t, which we are going to assume is a large time, then what we will experience is that the probability becomes time independent. And keep in mind again that this does not need to represent time, but this is just a nice way of understanding what is going on. So if we do this t times, then we reach a state which is called the most likely state or the stationary state or just the equilibrium state, where now the probability distribution does no longer depend on what happened before. And we normally call this for the steady state situation. And we see that this also becomes an eigenvalue problem, where the largest eigenvalue of this matrix T is the one which defines the final equilibrium distribution. So this is just a compact way of writing a Markov chain. So the way you can think of this now is as a set of, or chain of events, where we have our probability P here at a given time T0. And then we make this transition here of T0 going over to a T1. And we get a new probability distribution. So we have a P of 0 here, a P T1. And then we have a new one, where we now go from T1 to T2. So we have a T1 and then a T2. We have a new probability, P of T2 here. And this continues all the way till we have reached the most likely state. And this will be a T at the final time T. And then we have a T of T1, a sorry, let me just rewrite that one. To the final state T of T. And then we have a final probability of P of T of uppercase T. Now, these probabilities are now going to be rewritten in terms of what we call the conditional probabilities. So this T here, which you see, is the quantity which we now are going to train in a diffusion model. So we are going to set up a training scheme where we are going to have a simplified model for these probability distributions. This could be a Gaussian. And then we are going to make small steps between each T0, T1. So the length of the step size will have an influence on the way the training proceeds. And the probability distributions are going to be the same. So they would be, for instance, a Gaussian, or they could be a binomial. But what is going to be trained is the mean value of each of these distributions and the variance of each of these distributions, or better, the covariance matrix. So we are going then to assume that step by step here, there will only be small perturbations of these quantities. So the strength of the diffusion model lies in actually us rewriting everything in terms of small steps here, and then have a probability distribution which now is going to play the same role as an encoder. So in order to understand this, we are going to take an intermediate step. And that intermediate step is going to include a set of encoder transitions. So remember now that in the variational encoder, when we set it up, what we had when we looked at a variational autoencoder is that we had some original data set, which we called X here. Now this data set was then encoded by us setting up a probability distribution which transfers from X, the input data, to the latent data. And the latent data functions as a dimensionality reduction. So this is what we call the encoder. Now, this encoder then acts as a way to reduce the dimensionality of the problem into a latent space H. So this is the latent space. Now, when we have this latent space, when we have defined it, we would also, in that case, set up a probability distribution, which we call a prior, using Bayes' theorem. So this is something which goes back to 2 to 3 weeks ago. So we would then produce a probability distribution, and this had some parameters phi, which we need to train. So this probability Q is actually a simple probability which we defined, and that could be a Gaussian, for instance. Then we had a probability distribution here, which depends on the parameters theta to be trained. And this produces a so-called prior, which then is fed into the decoder. And that produces a new distribution, which is P of X, as a function of theta, given this latent space. Now, this quantity which you see here defines P theta of X of H, which is given by P theta of X, and this is just the product rule of probabilities defined by these quantities which we are training. So this is the decoder, and we set up the equations which are done in the training, and this gives us back an X tilde, which we obviously hope is as close to the real data as possible. Now, what we are going to do now is to actually break down the process you see here in many, many small steps. So the difference between a standard variational autoencoder and the diffusion models is that you can think of us now using a Markov chain to train this quantity here in many, many small steps. That means that this probability which you see here in a standard Markov chain is the one which now is replaced by the encoder part. But we are going to do this in many, many, many small steps. Now then, we will have a probability at this final time t, and then we are going to trace ourselves all the way back to the original distribution, which we want to reproduce. So we are going to look at these details after a small break here. So let's take a small break, and then we proceed with the derivation of the equations which need to be trained in order to set up a diffusion model. So before the break, we discussed the basic setup or a graphical display of the way we can think of a Markov chain. Now then, the other thing which we did was to remind ourselves about the setup of a standard variational autoencoder, where we now have some input variables X, so which are the data we would like to reproduce. And what we want then is to find a probability distribution, P theta, where we generate new X's by training a probability P theta. And just to quickly remind you of how we obtain that final objective function. So we have the P of theta of X, which is given by the integral over the latent space. So we have generated this latent space, which is supposedly a much smaller space than the one which encompasses all the input data. And then we multiply, or we integrate over X of H as a function of these variables theta. And this is something which we will then rewrite using the standard rules for the probabilities, for the multiplications of probabilities. So then we would have a P of X given H multiplied with a P of theta of H. So as we said, this part is normally called the decoder part. This is something which we would train with a given function for the probability distribution of the so-called prior. And this probability distribution then is the one which we have on the left-hand side. This is the so-called marginal probability, and this is the one which we want to achieve or obtain. And the hope then is that these variables which we are going to produce from that probability distribution, they are as close as possible as the variable which we gave as an input to the network. Now, when we now look at the diffusion models, and we apply this Markov chain Monte Carlo procedure, the way we can think of this is instead of just having one encoder, we are now going to stack variational autoencoders in a hierarchical way. So we are going to make a chain of such encoders, and we are going to set up what we will call a Markov hierarchy of variational autoencoders. Now, this type of system is not the one which we end up simulating in the stable diffusion models or this standard variational diffusion models, but it mimics quite a lot what we are going to do now. So suppose now that we have some probability distribution P of X. So this is the ideal which we want to have. And we mark that one with a point X here. And then we are going to set up an encoder, which now sets up the probability from going from X to H1. And here we can make a specific model. So we could label this with a P of X0 to indicate that this is the probability which we want. So this is our wanted probability, our final probability. And it plays the same role as the quantity which you see here. So we have this data set X0, and we use that one to map over to a new latent space, which we call now for H1 here. So this is now the latent space which we create. And if you go back to the design of an autoencoder, we have the encoder part where we now have set up the conditional probability, which is something which we last week and the week before we discussed in terms of a known probability distribution like a Gaussian. Then instead of now stopping and going back here with the decoder part, what we are doing now is to set up a new step. And then we produce a new H2 here, where we have a Q of H2 given H1. Sorry, let me just rewrite it because my handwriting was not optimal here. H2 given H1. So I'm now producing a hierarchy of encoders. And this now continues to the final step, which I'm just going to call for H of T. So instead of one latent space, I'm now going to have uppercase letter T latent spaces. So this just continues. And then finally, I have the final one here, which is given by Q of H of T of H of T minus 1. Now, all these probabilities now are going to be given by known functions. So a probability like this one could be given by a Gaussian or a binomial, or the probability distribution which we find the most relevant one. And the probabilities are going to be the same all the time. The only thing which will change will be the mean value and the covariance matrix. And these are parameters which then become hyperparameters, which we are going to, or parameters which we're going to train in the process here. Now, when we are done with that, what we will do now, since we have the latent spaces, we are now going to set up the decoder part in the same way as we did previously. So if you now look at what we did here, we have a latent space, And with the latent space, we have defined this prior probability because this quantity here allows us to set up the latent space. And when we have the H's here, we can then set up a model for the prior. And then this one is fed into the decoder part, where we now have this model for the probability here. And this one is the one which we train and optimize in the variational autoencoder. But now we're going to do this many, many more times. So what this one is going to produce now is its own decoder. And we could call this a P of H of T minus 1 given H of T. So now we are going back here. So that means that I have an input over here. And then here I have a new probability P of H of 1 given H of 2. And finally, I get that probability, which I call P of X0 of H1. And the one which you see here is the same as the one which we put up here, this quantity here. And that quantity which you see here, this one, is the one which we used in the determination of the final probability. So when we have this one, this X0 from H1 plays the same role as the probability you have here. And at the same time, we are going to use the probability P theta here, and we're going to break this down in terms of products now of many, many such probabilities here. So if you look at this one, which we are now setting up, this can now be written out in terms of a Markov chain, where this final probability is a product of all these individual ones. So if you now look back at what we did with the Markov chain, what we have here is a model through a variational autoencoder, a chains of stacked variational autoencoders, where we just do this many, many times. In our case, we're going to do this T times. That means that the final probability here, this P theta of X, which we want, our ideal, or Px of 0 as we wrote it here, is now going to be given in terms of a Markov chain, which is a product of all these guys. Now, one of the reasons why we do this, and this is something which leads to the mathematics of the diffusion models, is that the training becomes particularly simple when we now set up these changes in the mean values and the variances as small perturbations from one step to the next one. That means, again, that when we are training these models, we are assuming that this probability only change slightly from one step to the next one. That gives us, since we are using analytical expressions for these probabilities, something which can be analytically evaluated. And that is extremely beneficial. And this is one of the reasons why these diffusion models have become so popular. So what I'm going to do now is to go a little bit back to the Jupyter notebook, which we have, and look at the kind of equations which we can set up. So this is not going to be a complete setup in the same way as we did with variational autoencoders, with Boltzmann machines, and with GANs. But I just wanted to sketch to you the way these diffusion models are set up. The mathematics here is a little bit more involved in what you have seen before. And I'm going to refer to you to many of the technical details in the research literature. So let me now switch back to the Jupyter notebook. So the thing which we have done now is the following. So we can now, if we now look back at these images, you can now set up not the way the diffusion model is going to look, but the hierarchy of Markovian variational autoencoders. So the first step which we're looking at is a step where we now have these Markov chains of variational autoencoders. And every step can be thought of as an encoding function. And then when we are going back to the final distribution, we have a decoding function as well in terms of well-defined probabilities. So each transition down this hierarchy is Markovian in its sense. So it only keeps memory of the previous step. And then we decode each latent set of variables in terms of the previous ones. So you can think of this, if you look back at the figure which we put on the whiteboard, as simply a stacked set of variational autoencoders. And if you look at the figure, this is a repeat, except that in this figure, which I borrowed from this article, which I highly recommend, which gives a very nice connection between diffusion models and variational autoencoders. Here, my H's, so I've used H for the latent space, is given by the Z's here. But this is essentially what we put on the whiteboard. And what we would have then is a Markov hierarchical variational autoencoder with T different latent spaces. So this is the final one. And the generative process is modeled as a Markov chain where each latent HT is generated only from the previous one. So in this case here, you see now that when we move back, this contains information from the step T+1. So we are going from this one to the next one, etc., etc. So if you then look at the mathematics which we want actually to end up with this probability, which when we write it in terms of the standard product rule of probabilities, is now going to be given by the one which represents the final step. If you now look at this image, this means this one. And I have H instead of X, sorry for that. Then I have my prior at the step H of T. So I'm simply using the Markov chain here because this now contains the product of all these other transition probabilities or these conditional probabilities. And the late or the encoder part, which has a set of parameters theta, which we are training, and not phi, which we are training, is then simply given by the first one, which if you look at this image, is given by this step here. And in my notation on the whiteboard, I used X0, which is the one we want to have. So this final probability here, when we then integrate away the H's, is actually the quantity we want to have. So if you look at this quantity here, then we go back and calculate the marginal probability, and we calculate the log of the marginal probability. So that means that what we want now is this quantity here, but now integrated up over all the encoder or the latent variables. So that means that what we have then is the log of this quantity here, where I now simply just multiply with 1. And keep in mind now that this is getting a little bit more complicated. This is a chain of probabilities, or chain of these marginal probabilities for the encoding part. And this can be calculated analytically when you now plug in a well-known probability distribution. So in principle, what you end up with is actually to calculate the expectation value of this quantity. And we show that this quantity here is actually larger or equal to the expectation value of log of this quantity. And this is something which we derived last week when we studied what was called the evidence lower bound. So this, as it stands now, is not the way a diffusion model is implemented, because there are going to be some approximations which we need to discuss now. But basically, if you want to train what you could call now a stacked set of variational autoencoders, you would actually have to optimize this function here, this expectation value. And you would then have to set up models for these quantities and perform the products here, and then also calculate, perform the Markov Monte Carlo chains of these probabilities multiplied with each other, and you would have to perform this as a stochastic Monte Carlo sampling in order to calculate that specific expectation value. And the probabilities which generate these new events are given by these encoder probabilities. So feel free to ask questions. So this is basically a simple way to understand the entry point to the diffusion models. So what you would end up then when you spell it out is to calculate this expectation value here. It doesn't look so nice. So one of the ways this can now be modified is to add some constraints or some restrictions on these probabilities and the dimensionality of the spaces. So what we have here is what you can define as a stacked set of variational autoencoders, or what you might call a Markovian hierarchical, because you have a hierarchy. This just follows from H1 to H2 to H3 and so on. So that's the hierarchy. And so in a certain sense, it looks like a recursive network, or recurrent neural network. But then in the diffusion models, there are some additional constraints which are put in. So the latent dimensions, so remember when we do a variational autoencoder, the whole idea is that the latent space is much smaller than the real data space. So in this specific case, what we have done, or what is done, is that the latent dimension is exactly equal to the data dimension. The structure of the latent encoder at each time step is not learned. So it's given by a predefined Gaussian model, or if you're dealing with a binomial function, you could replace a Gaussian with a binomial. But in general, people use a Gaussian, and it's a Gaussian distribution centered around the output from the previous time step. So it's useful now to use time as a kind of way to distinguish the different steps which we have. You don't need to think of time, but I'm going to use time because that falls naturally in this discussion. And the Gaussian parameters of these latent encoders, they may vary over this time, this artificial time, in such a way that the distribution of the latent at the final time step is a standard Gaussian. So the posterior, which we end up with then, is simply given by this chain here of all the probabilities, the transition probabilities, or the probabilities of going from one step to the next one, starting with this x0. So this is the same as the quantity which we defined up here, this quantity. So I'm just introducing a slightly more compact notation. And now the thing is that the distribution, if you now look at the second assumption, the distribution of each latent variable in the encoder, so each one of these is the encoder part, is a Gaussian which is centered around its previous hierarchical latent. Here then the structure of the encoder at each time step is not learned, it is fixed as a linear Gaussian model. And where the standard deviation and the mean value can be set beforehand as hyperparameters. So you can have them fixed throughout the calculation, or they can be learned as parameters. So that means that when you parameterize your Gaussian encoder, you would encode it with a mean value, which now depends on a parameter alpha, which you would vary. So that becomes a learnable coefficient. And this is multiplied, so there is a slight modification of the mean value in terms of this previous value. And then there's a variance, which is simply given by 1 minus this alpha of t as a parameter times. So that means that the covariance matrix is diagonal. And the forms of the coefficients are chosen so that the variance of the latent variables stay at a similar scale. So we want this process to be a variance preserving process. So there are tons of variations of this. So what I'm setting up here is just a type of approach which is going to allow us to perform calculations, but there are actually many modifications to this parameterization of the Gaussians. The main takeaway is that this alpha of t is a learnable coefficient that can vary with the hierarchical depth t, so that gives us some flexibility in the training here. So mathematically, these encoder transitions, they have a fixed form. So they are now given by a Gaussian, reflected in this letter n, with an x of t as variable, mean value, which is given by this trainable parameter, and finally the variance, which is now simply given in terms of this parameter alpha t here, 1 minus this alpha t. So this is gives us a mathematical expression which is going to allow us to simplify the calculations. Now, from the third assumptions, this alpha t evolves over time, so it's a parameter which will change. You can think of alpha being changed perturbatively from time to time, and it evolves according to a fixed or learnable schedule, which you can structure such that the distribution of the final latent, this p of x, is a standard Gaussian. You can then update the joint distribution of a Markovian variational autoencoders to write the joint distribution for a variational diffusion model in the following way here, where now this px of t is actually given by a Gaussian with the zero mean value and a variance which is equal to 1. And this is then defined in terms of this x of t here, which is the last latent value. So in a sense, what we end up with is something which looks like this, and it acts as a kind of denoising. So collectively, what this set of assumption describes is a steady noisification of an image input over time. So you progressively corrupt an image by adding Gaussian noise until eventually it becomes completely identical to pure Gaussian noise. And then we have the decoding part, where we now are just stepping ourselves back again, and then we need to find a training procedure for this probability, which you have here, the probability P. And that's the next step. So the next step, when we're now setting up this modeling here, so this encoder function is then known. They are no longer parameterized by some parameter phi, as we had in a variational autoencoder, as they are completely modeled as Gaussians with a defined mean and variance parameters at each step. Therefore, in a diffusion model, or what is often called a variational diffusion model, we are only interested in learning the conditionals, these conditional probabilities, so that we can simulate new data. So at the end, as we said, if we now go a little bit back again, if you look at the training, what we want to learn is this quantity here, because that quantity is the one which we use in the final stage here to calculate the final probability P of X. So that means that what we want now is to set up a training procedure where this is the quantity we are going to optimize. And that means that the derivatives we are going to take when we calculate the gradients are the gradients of this quantity here. So we haven't mentioned the calculation of the gradients yet. So, but the aim of this session here is to give you the overarching picture on diffusion models. And we are not going to set up codes in this course for this year on diffusion models. So, but setting up everything means that now we need to set up the training. So we are back to the basics here. So we want this quantity here, Px, which now is this x of 0, which is the final time. So if we go back a little bit, so we want now to integrate that part. We calculate the log of it, as we did with variational autoencoders. So it's very much the same procedure. And then we are simply rewriting this in terms of the different functions. So we know that we've just multiplied with 1. So we have the encoder part, which is coming in here. And when you admire these lovely equations, you can actually show that this equation here This is actually called Jensen's inequality. So this Jensen is not a relative of the present person here. I'm not a relative of mine. It's another Jensen, actually quite many Jensens in the Nordic countries and elsewhere. So the final equation then, which we are going to set up, is this quantity here, which we want to evaluate. So you can split this up again, and that means that we can rewrite, if you look at these equations here, in terms of the Kullback-Leibler divergence. So when we rewrite these terms, if we just proceed here, this is not very exciting, and I have borrowed many of these things from that work by Calvin Luo. We end up with the final expressions, which are these terms here, this first term, the second term, and the third term. And these can be, if you now look at these expectation value, this term here can be rewritten, this one, as a Kullback-Leibler divergence, and the same with this term here. And that means that I can rewrite this first term, which you see, is normally interpreted as a reconstruction term, which predicts the low probability of the original data sample given the first step latent, so which is this term here. And this term also appears in a standard variational autoencoder and can be trained in a similar way as we did in our discussion with variational autoencoders last week and the week before. So you see the diffusion models have lots of commonalities with the variational autoencoders. They can be seen as actually stacked variational autoencoders with some specific constraints. So this quantity which you have here, since we now are looking at the prior, which is this p x of t, that is normally called a prior matching term. And this is a quantity we minimize when the final latent distribution matches the Gaussian prior. And this term requires no optimization as it has no trainable parameters. And furthermore, as we have assumed a large enough t such that this final distribution is a Gaussian, this term effectively actually gets as close to zero as you can get. So this is something which you normally would not deal with. So if you look at the last term here, that term here is again the expectation value of a Kullback-Leibler divergence, and is normally called a consistency terms. It tries to make the distribution at x of t consistent from both forward and backward processes. And it's normally called a denoising step from a noisier image, and that should match the corresponding noising step from a cleaner image for every intermediate step. And this is again reflected mathematically by the Kullback-Leibler divergence. And this term is minimized when we train the probability to match a Gaussian distribution. So you see the advantage of using a Gaussian distribution here. Again, we are not going into the details of how to implement a diffusion model. There are links at the end of the slides here where you can actually look at how this can be implemented with TensorFlow. There are also PyTorch examples. But this is the kind of basic step which you would then have in the training of the variational diffusion models. And if you look back at the equations here, you see now that we are training these parameters together. And this is reflected in the colors which you see here, so that this probability is then set up with this probability distribution here in terms of the Kullback-Leibler divergence. And the cost of optimizing a variational diffusion model is primarily obtained by the third term, since we must optimize of all time steps. And under derivation, all the three terms are computed as expectation values, and that means that they can be approximated using Monte Carlo estimates. So this estimate evidence lower bound optimize, when you're optimizing the terms we just derived, it may not be optimal because the consistency term is computed as an expectation over two random variables for every time step. And the variance of this Monte Carlo estimate could then potentially be higher than a term that is estimated using only one random variable per time step. So there are many modifications to the equations which you see here in the training. And I encourage you to take a look at more details and implementations in this article by Calvin Luo, from which I have borrowed quite some material and actually gotten, hopefully, a better understanding myself. So we are not in this course going to implement through codes the diffusion models, but if you're interested in implementing them in the second project, I mean, I encourage you to do so. And if you then scroll back and go back to the very beginning and look at the codes which we have available, if you then go into I should have them, where did I place that one? Yeah, if you go into the textbook by Foster and look at chapter 7, there is a advanced implementation of different diffusion models in chapter 7 of Foster's textbook. So that means that if you go to this GitHub address, which you see here, you will find TensorFlow implementations. So if you go back to the notebooks and then go into sorry, it was not chapter 7, but it's actually chapter 8, you will find several implementations of diffusion models here using TensorFlow. So if you wish to explore that, I mean, take a look at the chapter 8 and the codes which Foster has placed there. There are, if you search online, you will find diffusion models written in PyTorch. And I invite you to take a look at these codes here. So this part is now ending the regular lecture sessions for this course, for this semester. And next week, we are going to have a summary where we are simply going to put together everything which we have gone through in this semester here. So this summary will be done on Monday next week from 10 to 12. And that is mainly because there is a very interesting workshop running where some of you will participate, which begins on Tuesday and ends on Thursday. So that means that the lecture which we have on Tuesday next week will be moved to Monday from 10 to 12 next week. And again, if you cannot be there in person or you cannot attend the Zoom session, you can always watch the registration or the recording of the lecture. So this ends the more lecture part of the course, and then we will have a summary next week.